Hey there, everyone. This is a video on chapter 9, basically inferences for two samples, or basically from two samples. In chapter 8, we did one sample hypothesis testing. Now we're going to turn our attention to two sample hypothesis testing. So we have two proportions we'll do. We'll talk about doing two means, independent samples. We'll talk about doing two dependent samples, meaning matched pairs. That's basically what we're going to do here in chapter 9, okay? 7 and 8, we introduced methods for basically testing of inferential statistics, or how we can find those things. Chapter 7, we presented methods of constructing confidence interval estimates of population parameters. Chapter 8, right, we did testing claims about a population parameter. And now in 7-8, basically involved a single population, basically a sample from a single population. We're now going to turn our attention to doing basically two samples, or basically two sets of sample data, instead of just one. For the types of tests we might do. So test the claim, for example, that when college students are weighed at the beginning and the end of their freshman year, the differences show a mean weight gain of 15 pounds. That's actually an example of matched pairs because you're using the same individual and you do a before and an after. That's 9-4. Test the claim that the proportion of children who contracted polio is less for children given the Salk vaccine than for the children given a placebo. That's two samples, and you're comparing those two samples. Test the claim that the subjects treated with Lipitor have a mean cholesterol level that is lower than the mean cholesterol level for subjects given a placebo. Again, two samples. All right, so 9-2 is two proportions. You guys should be pretty comfortable with proportions by now, but you'll see basically we're going to tackle this. We'll be able to construct a confidence interval. We'll also talk about how we can do hypothesis testing for these, right? So some of the notation that you need to get familiar with right off the bat, you'll see for population 1, as we'll define it, you'll have P1 is going to be the population proportion, N1 is the size of the sample, X1 is the number of successes in that sample. Again, you can find P hat then by doing X1 over N1. And Q1 hat is going to be 1 minus P1 hat. You'll note that the corresponding basically notation is the same for population 2, except for everything is noted with a subscript of 2. So one thing that we might talk about is the pooled sample proportion. And that's going to be basically the number of successes in the sample 1 plus the number of successes in sample 2 divided by the total sample size in sample 1 plus the total sample size in sample 2. And that'll give you P bar. Again, orders of operations, make sure that you add these two up here together first. And these get added together. Some of you guys might forget to put parentheses in, and your calculator will just do X2 divided by N1. And then add N2 plus it and have this plus it. Okay, so just be mindful of that. All right, so some requirements first. We have proportions from two independent simple random samples. Independent meaning they do not depend upon each other. They are separate. 2, for each of the two samples, the number of successes is at least 5 and the number of failures is at least 5. That should seem kind of similar to what we've done before when we did the binomial probability distributions. So the test statistic, finally, for two proportions. So the null hypothesis is that the proportion from population 1 is equal to the proportion from population 2. And you'll see our test statistic comes from the standard normal distribution, hence the Z right here, meaning standard normal. P1 hat minus P2 hat is our first part. This should look almost identical to what we've done before for basically proportions, except for we just added in a little more complication now having the two samples. And down here you have P bar and Q bar. If we go back a couple of slides, again, this is what P bar is and this is what Q bar is. So you want to write those down in your notes. It'll be helpful to have. Sorry. There we go. Back to the test statistic. Now, one thing you might be wondering is P1 minus P2. If you take and rewrite this P1 equals P2 by subtracting P2 to the other side, which is what we have down here, you'll see that it equals 0. So a lot of times this is going to be assumed to equal 0. And so all you really do is calculate this and then divide it by this square root. So testing two proportions, the p-value method, p-values are automatically provided by technology. I would say that this is going to be very helpful for you guys. If you don't have technology, you can actually use the table A-2, which is your standard normal distribution table, to solve it as well. And the critical values, you can use your standard normal distribution to solve that as well. So Basically, the same exact procedure as we did learn in chapter 8. So confidence interval estimate of P1 minus P2. So again, you'd have basically your P hat, if you think of this, minus E. You can think of this as just P hat plus E, which is the same exact thing we did previously when we just did one sample. And now we're doing two samples. We'll do this subtraction of P1 hat minus P2 hat, and then we'll minus the margin of error. Now, the margin of error is going to be Z alpha over 2, which again is standard normal distribution, times the square root. And you'll see now this is going to be P1 hat times Q1 hat divided by N1 plus P2 hat times Q2 hat divided by N2. All right. Now, let's go to the example. And again, you can pause the video at any time. Do people have different spending habits depending on the types of money they have, right? So a lot of times there is this conjecture that if I was to give you a $100 bill, and it was a $100 bill versus a $101 bills, you'd be more likely to save that $100 bill than spend it because you don't want to break that $100 bill maybe. Or maybe you just think, oh yeah, it's a little harder to spend it, so I'm not going to spend it. But if I was to give you that $101 bills, you're more likely to spend it all, right? So here they did an experiment on 89 undergraduates. Were randomly assigned to two groups. One was given a choice of keeping the money or buying gum or mints, right? The claim is that money in large denominations is less likely to be spent relative to equivalent amount in smaller denominations. Let's test the claim using a 0.05 significance level. Oops. Below are the sample data and summary stats from it. So we have group 1, subject was given a $1 bill, and in group 2, subject was given 4 quarters. Okay, so this is the number that spent the money, and this is the subjects in the group. And so obviously P1 hat then is X1 divided by N1, and that's this 12 over 46. P2 hat is going to be this X over N, and that's how we get P2 hat. If we want to get P bar, we'll add the number of successes, 12 plus 27, and then divide by the total sample size. Okay, we got to do some requirement checks, make sure that it came from basically a simple random sample or that these are independent random samples. 2, the subject given the $1 bill include 12 who spent it and 34 who did not. The subjects given the quarters include 27 who spent it and 16 who did not. So do they have 5 successes and 5 failures? Yes, so we're good on that front. Step 1, take the claim, right? Money in large denominations is less likely to be spent. And so if we want to say that, basically P1 is less than P2. In other words, P1 is the proportion that were given the $1 bill, and P2 are the ones that were given the quarters. And so the expectation is that the proportion that spends it, P2, is greater than P1. Now, if we want to make that false, it'd be greater than or equal to, and you see that the equal sign's there, so that's going to be your null. Then you have your alternative as your claim, which is great. This is going to be a left-tailed test. And one-sided. We have our significance level that we picked. We're going to use the normal distribution to run the test. And this is our test statistic. You may want to type all this into your calculator, make sure that you get it correctly. And it makes sense. We get negative 3.49. And 2 ways of showing this. One, graphic figure A right here has the p-value method. So in other words, if you use technology, it spits out a p-value of 0.0002. You could probably also use your table to get a ballpark estimate of it. And you'll see that it is very small. And therefore, because it's smaller than the alpha value, you would reject the null in favor of the alternative. And in the critical value method, you would compare it to negative 1.645 because that is our alpha of 0.05 in the left part of the tail. And your test statistic lies in that red region, which is the rejection region. So because the p-value is less than the significance level, we reject the null hypothesis. Same thing with the critical value as well. So you might conclude there is sufficient evidence to support the claim that people with money in large denominations are less likely to spend relative to people with money in smaller denominations. Okay, one other thing that should always be noted whenever you're doing studies like this, in fact, I can't remember the acronym right off the top of my head right now, but there is an acronym for basically using undergrad college students because they are all of some type of demographic. Right? They're going to school because they value education or whatever it might be. So it should be noted that these subjects were all undergrads and care should be taken before generalizing this about the general population, right? So we can also construct a confidence interval to estimate the difference between the population proportions. A note of caution, the standard deviations based on estimated values of the population proportion and the hypothesis test are different. So you can end up with different conclusions between these two. So constructing a 90% confidence interval estimate of the difference between the two population proportions. What does the results suggest about our claim about the people spending large denominations relative to spending small denominations? So if we go about and construct it, so we get our margin of error, and we'll have to do our P1 hat minus our P2 hat, would be the piece that we're going to minus the error from and add the error to. Right? So that'll be this piece right here. And we'll subtract the error, and you'll see that we get negative 0.528 and negative 0.206. 0 is not included in here. In other words, the null hypothesis is not between these two values. In other words, implying that there is a significant difference between the two proportions. And so there does appear to be a sufficient evidence to support the claim that money in large denominations, again, is less likely to be spent relative to the equivalent amount in smaller denominations. The P1 hat minus P2 hat can be approximated by a normal distribution with P1 minus P2 and a variance of basically the two variances added together. And that's basically how we have P1 times Q1 divided by N1 plus P2 times Q2 over N2. In other words, the variances of the differences between the two independent random variables is the sum of their individual variances because they're independent. So again, the preceding variances leads to basically, if you take the square root of both sides, whoops, other way, you take the square root of this, square root of this, that'll give you basically this. So we now know that the distribution of P1 hat minus P2 hat is approximately normal with a mean of P1 minus P2 and a standard deviation is shown above. So the Z test statistic has the form given earlier. So when constructing confidence interval estimates of the difference between the two proportions, we don't assume that the two proportions are equal, and we estimate the standard deviation as this. So, and the test statistic, use positive and negative values of Z for two tails and solve for P1 minus P2. The results are limits of the confidence interval given earlier. So that's 9.2, pretty quick, short and simple. Feel free to ask me questions about 9.2 if you have any during office hours.